All right, here we are for the last part of Chapter 8. So we're going to look at a few different diseases here. The first one is tuberculosis. Your book has picked a few of the diseases that are very common globally, even if they're not necessarily common to where you and I live. And I realize that everyone in this class is from different places, so that doesn't always apply either. So tuberculosis is massive. I mean, a third of the world's population has been exposed to TB. A third of 7 billion people. Just let that sink in for a minute. That's huge. Tuberculosis is caused by a bacteria. It is transmitted through coughing or sneezing, sometimes called respiratory droplets. And once you have it, part of the reason that it's so globally spread around is that there is a latent form of TB. And while you have that, you have no feelings of being sick. You don't feel sick. You don't even know you have the disease. You're not contagious during this time, but you certainly can move around the world and interact with other people. And you have the bacteria inside of you, and it gets into your lungs. And so here's our little bacterium. And what happens is your white blood cells come and kind of form, this is rudimentary here, but they kind of form this little barrier around it. And this whole structure is called a tubercle. And that's just hanging out in your lungs. The tuberculosis is contained, but if you get sick, those white blood cells essentially are called off to take care of other things, and the tuberculosis can kind of break through the tubercle, and then you have the active form of TB. And when you have the active form, you have symptoms, you are contagious, and it can spread to others. During that form of tuberculosis, you might be coughing up blood. This is what used to be called consumption. So it's what people thought, basically consumed you from the inside out, because people would lose a lot of weight while they were experiencing it. It's referenced in a ton of movies like Moulin Rouge, so you can keep your eyes open for that. Malaria is another disease globally that's pretty massive. There's over 200 million cases per year. The cause is something called plasmodium. It's a little protist, and it's transmitted through mosquito bites. So instead of through breathing on people, the plasmodium gets in your blood, and then if a mosquito comes and bites you, it could get into their system and as a secondary host. And then when that mosquito bites someone else, it actually goes through their saliva and gets into your blood, and now that you would be infected. So symptoms of malaria are having flu-like chills and fever, so it's why it is actually relatively easy to misdiagnose it, or why people might not realize they have it right away. The treatment, once you've identified it as malaria, is to take drugs that attack the plasmodium and just directly go after the pathogen. And of course, you and I might think that's easy to do, but of course, if we're looking at where malaria is occurring, buying a drug when you don't have health insurance or even the option of insurance is much too expensive for many of these folks, and so that's where we see it leading to death. So prevention is to eliminate mosquito bites, either by preventing their breeding or preventing them biting you. That's where all of our prevention efforts are going. So to prevent them from breeding, sometimes we will spray, and there's environmental impacts with this, but sometimes we would spray certain swamps or areas where mosquitoes are known to breed with a pesticide, an insecticide. There are some people out there hoping to genetically modify mosquitoes, male mosquitoes that are sterile, so that when the female mosquitoes mate with them, there actually is no offspring that's produced from that. So that's been suggested. I don't believe any of that has actually been released into the wild, but it's an idea that's out there. And then the other idea is to prevent biting, and so this is why we have things like bug spray and mosquito nets. These two particular pictures are from my time in Rwanda when I was in a malaria, an area that was at risk for malaria, so I took preventative drugs and then also had mosquito nets. So malaria is absolutely fairly global, and it's a tough one for us to crack, because when we have gotten rid of it, we've done it in ways that are pretty detrimental to other parts of the environment, and so we're trying not to repeat that, and so it's posing a challenge. Influenza, of course, is the flu, is what we're used to, and the flu, this tends to surprise people. There's about 36,000 fatalities every year in the United States alone from the flu. 36,000 people die from the flu. This is why flu shots are important, because of that herd immunity concept. Okay, so the virus for the flu, it's caused by a virus. It has H spikes and N spikes. And that's why there's things like H1N1 or H1N5. It's just that the way that we've numbered the spikes. So that's where those names come from. Obviously, it's caused by a virus. And transmission is again through those respiratory droplets, coughing, sneezing, but also contact with objects. It is possible, you know, if you blow your nose and don't wash your hands, or if you wipe your nose because you know you're in a hurry, you don't have time to grab a Kleenex and something's coming, you know, but then if you accidentally touch something after that, the virus can survive on that surface for an amount of time, and if someone else were to come in contact with it and then brush their face, maybe with their hand, brush their hair out of the way, or, you know, pick something up to eat and then put it in their hand, put it in their mouth, you know, that could enter the body. So a couple ways that it can be transmitted. The symptoms of the flu are runny nose, a cough, chills, fever, nausea, head and body aches. So that's kind of, you know, most people have had the flu, so that's what we're looking at for symptoms. The treatment, because it's a virus, an antibiotic is going to be useless. Antibiotics are only good for going after bacteria. So with a virus, basically we need to let your body do the work. So getting a lot of rest so that your body can just put all of that energy, put all of that ATP as much as possible into the immune system, fighting the virus, making you comfortable so that the immune system can really just do its job. Prevention, of course, is the vaccine. We have a flu vaccine. Some people say like, oh, I'm totally vaccinated, but I don't get flu vaccines every year because they never seem to work. And I've heard that so many times. And I get that. I understand where that logic is, but to just walk through it real quick, you know, again, we're talking about 36,000 people dying. So if there's something small that you and I can do to try to prevent that, you know, to me that's perspective, but some people don't care for vaccines, and for that reason, not for that reason, but because they're against it for other things. But this vaccine, there's so many versions of the flu. So those viruses, like we said, have H spikes and N spikes, and there's a ton of different varieties of that. And basically, the flu vaccine is, the people who are epidemiologists are basically trying to predict which variety will be most common that coming year, and then that's the vaccine that they make for that year. And so you could be vaccinated against that, and you could come in contact with that flu and not get it because your vaccine's working. But if you happen to come in contact with a different version of the flu virus, you would then contract that. And so that's why it might seem like your flu vaccine isn't working, but it's just because of all the different strains. And just like HIV, where that virus was mutating so quickly that making a vaccine was almost impossible, with the flu it's possible, but it's not possible to have a vaccine to protect against every single kind of strain of virus. So certainly it's not going to protect you against everything, and I understand that, but it is a small thing that's usually pretty easy to find at work or school for a relatively reasonable cost. So looking a little more at the flu viruses, we can see that they can mutate a couple different ways. We've got our capsid, we have our spikes on the outside, we have our RNA on the inside. And we could see that it's possible that maybe we just have a mutation in that RNA, and then maybe we'd have a second mutation. And you can see as a result of that mutation that the spike changed. Over here it was all yellow, but because of that mutation, this spike is now blue. So that's one way. We could just have a spontaneous mutation. Another possibility is that viruses could come into contact with each other inside a human host. And this is how things like the bird flu were able to transfer from being just in birds to being in humans, is that within a host cell, someone had the bird flu virus and someone had the human flu virus at the same time, and those cells were essentially able to fuse together and exchange DNA in each, or RNA in each direction. And as a result, what came out of that was a combination virus, where it had both types of RNA from both types of bird flu and human flu. And as a result, we have spikes that are a combination that can then interact with your cells and also interact with avian cells. So, what we've talked about are some diseases that are very well known and have been around for a long, long time. But we do have something called emerging diseases on this planet. And emerging diseases are diseases caused by pathogens that are newly recognized within the last 20 years. So these are things like avian flu and swine flu and SARS and MERS. There's some others too out there, Zika virus, right? Those are all things that are new within the last 20 years. We didn't know about them before. And part of it could be that it's the result of a mutation, like we just talked about. Another contributing factor is that the more and more people we have on the planet, the more we are diving into new areas, new wild areas. We're cutting down trees and moving into forests where people may have never been before, or even if they were, there was just an individual person. So we're increasing our likelihood of interacting with these diseases that may have been there, but previously weren't actually coming into contact with humans. And then another concern, of course, is that with international travel, there's just the ability for these diseases to spread a lot faster and become more of an outbreak or a pandemic. Re-emerging diseases are diseases that have reappeared after a significant decline. So because of vaccines and sanitation, we've seen that go down, but now they're reappearing after being at minimal levels for a while, especially with people not taking vaccines. We've seen that start to increase again. And then where we want to end for this chapter is looking at antibiotic resistance. And this is really, really, really important. So penicillin was introduced in 1943, and 4 years later, we already knew there was resistant bacteria. So within 4 years, there was bacteria that had mutated enough to be resistant to this particular antibiotic. Now, keep in mind, as a human, at the earliest, you can probably reproduce in 12 years, versus a bacteria is going to do that in a number of hours or days. So bacteria absolutely have an advantage over us in that their reproduction is just so much faster than human. So, in antibiotic resistance, I have to make this point. The pathogen, in this case the bacteria, is becoming resistant to the antibiotic. It is not that the human is resistant to the antibiotic or that the human is resistant to the bacteria. I see that mistake very often. This is the only way to define it. The pathogen, the bacteria itself, is resistant to the antibiotic. So that bacteria is much more dangerous to you and I because we do not have a tool, we would not have an antibiotic to then kill it, and it would be more likely it could overcome our immune system. And that is what we've seen with some of these. So antibiotic resistance has been seen in resistant strains of the TB bacterium and in the Staphylococcus aureus. Those bacteria have some strains that are resistant to bacteria. MRSA is multiple resistant Staphylococcus aureus. So it's resistant to multiple antibiotics. So if you have a MRSA infection, essentially your body is left, your immune system is kind of the only thing left to fight it. We, as humans, as doctors, we have nothing left to help you because the type of bacteria you happened to come in contact with is resistant to all of the tools that we normally could use to fight it. So it's a little scary. It absolutely is. You've probably heard about antibiotic resistance before. So the big question is like, well, what do we do? Do we just stop using antibiotics? Do we just let things go as they're gonna go? Or what can we do about it? And the best way to fight antibiotic resistance is to use those antibiotics wisely. There's a couple of things to do here. So the first one is that if you have a viral infection, and your doctor knows that, don't ask for an antibiotic because it will do absolutely nothing to help you. What it will do is increase the amount of antibiotics that bacteria are exposed to and make it more likely that something in contact with that would, if already resistant, become more common. So only use antibiotics when you know you have a bacterial infection. And when your doctor knows you have a bacterial infection and they prescribe an antibiotic, take it as long as they say you're supposed to, and don't cut it short. Even if you feel 100% better and you're like, hey, I'm totally healthy, I don't need to take it anymore, you still have to take your antibiotic. Because if you don't, that's where the resistance comes from. So here in this image, we see what's going on. In the black, we see not drug-resistant bacteria, and in the tan, we see drug-resistant mutant bacteria. So essentially what's going on is, let's say you start taking your antibiotic, you start exposing it to the drug. So we start killing off these non-resistant types, and we kill them because your immune system's helping too, but we're just helping your immune system out. We're giving it a little extra boost, right? So you destroy those, and later on in your antibiotics, right, you decide to stop taking your antibiotics. You're like, hey, I feel totally fine. I don't need to take it anymore. And that's this stage. When you feel fine, that's because for the most part, you've killed most of the bacteria. It's no longer a massive drain on your body, and you feel okay. But you still have these bacteria that did not die. They did not die when you were taking that. If you kept taking your antibiotic, then they wouldn't be able to resist it. They would have been exposed so much to the antibiotic that they would also die. But if you don't take your antibiotic, they still survive. And now that you've stopped taking your antibiotic, they are able to reproduce and reproduce and reproduce and reproduce, and now your infection comes back. But this time, it's resistant to the drug. Okay, it always was resistant to the drug, but now the whole population is, almost the whole population is resistant to that drug, and that drug you previously took will no longer help you fight that infection at all. Okay, so a couple of things here. The first is that, again, the pathogen is becoming resistant to the antibiotic. The second thing is that this has to already exist, this resistant mutant has to already exist at the time of your infection in order for this to even happen. The biggest misconception that I see all the time is we use antibiotics so much that the bacteria become resistant. That is a false statement. The bacteria has to have already had a mutation, making it resistant to the antibiotic at the time that it is exposed to the antibiotic, to then continue that line or that strain of resistant bacteria. So whatever you do, do not say that exposure to the antibiotic makes the bacteria resistant, because that's absolutely false. It is that a mutant bacteria has to already exist, just purely by luck. It's just purely by chance. It already exists, and then when it is exposed to the drug, the drug has no effect on it. Therefore, it becomes more common in the population. It's able to survive and pass on its resistance to all of its offspring. Because remember, we're just doing binary fission. We're just making copies of it. So that is antibiotic resistance. So if you get an antibiotic for a bacterial infection, take it to the end of its time, tell all your friends, and don't ask for an antibiotic if you've got a viral infection, because unfortunately it won't actually do anything, and it'll just make antibiotic resistance more likely. All right, there's infectious diseases for you.